So we now move to part 2 of the lesson on ARIMA modeling and forecasting. And in this part, we are going to do a complete example with preliminary steps and the model fitting and then forecasting, watching the plot of the forecast and so on. I must confess before I start that I did a little bit of model fishing so that we wouldn't waste too much time. And you should be aware that this modeling process is an iterative process and you don't get it right usually the first time, okay? So I'll tell you what I mean by that in a second. Also, let me put some live transcript so that I forgot to do that in the first video. All right, so we're going to show an example with all the steps of ARIMA modeling without worrying about the math involved in writing the forecasting model, which is the whole algebra exercise that we'll do on Thursday. How to write your model, how to write the forecasting model, how to translate all the ARIMA algebra into a beautiful regression model, okay? And then we are going to see the steps involved are pre-transformation, again, differentiating to remove trend, mean and seasonality identification, model fitting, residual analysis, forecasting, and then the measurement of the forecast error. And if all that is no good, we go back and start again, okay? Which we won't do today, but I want you to be aware that the first time it's not gonna be pretty. So why is it important to know all that? Well, ARIMA models usually are gonna be better than other models when it comes to forecasting. They're very simple. You probably will not agree after you see the algebra, but they are. And it's very important to be able to compare their forecasts with those of the other modeling strategies. And then ARIMA is an essential tool in the forecast practitioner toolbox, and getting experience in doing all the steps requires doing many examples to practice, okay? It takes practice and takes a little time. So let's put an exercise here. Let's see. They come to you with this problem. You are now an expert practitioner in forecasting, and they say, oh, okay, I'm Travelers Rest Incorporated. I have 4 hotels in a Midwestern city. And we want to develop a model that will forecast what's going to happen next year, every month of next year, okay? So we need a forecast because we need to prepare our recruiting, how many people we are going to have to hire, how many resources we have to buy, how much food, and so on, how many towels, and so on. And that takes time, right? And if it's in the COVID period, it's going to take even longer time, right? So they have data, of course, and these days, even more data, right? These days, hotels have data like every other company. The available historical data consists of the number of occupied rooms during each day, okay, for the previous 15 years. And they have data from January 77 till December 1990. But they want monthly forecast. Okay, it doesn't help the hotel to have a day-to-day forecast because that could be even more variable than the monthly one. So they want to have a monthly forecast. So they just calculated for us the monthly averages by dividing the monthly total number of occupied rooms divided by 12, okay? And that's not even a moving average. It's just a way of aggregating the data for us. So they gave us the average monthly number of rooms, of occupied rooms every month for 15 years. And so we decided first what will be our training period. So we decided the training period will be the first 14 of the 15 years. So we will have monthly data for 14 years, and we will forecast the 15th year. They are asking us for a model. We want to give them a good model. So the first thing we want to check is that the model is going to be validated, right? When we validate it, it does well. So we want to validate it with the test data. And the test data is going to be the last 12 months of the last year. And so the 1990 months are the ones that are going to be forecasted, and the forecast is going to be compared with the data for 1990. And if that's good, then we might give them, if that's good and the model is good, of course, there are several things involved, then we'll give them that model, charge them $1 million or something, and then be happy with that, okay? So our test data will be 1977 to 1989. So these are decisions you have to make, depending. You have to customize, depends on what your customer wants, right? What your boss wants, what your company wants, what your institution wants. So we start by plotting the training data, okay? So we look at the time plots, we assess that there is variance non-stationarity, as we can see in this first plot, right? Variance non-stationarity. And so we try several transformations, the log, the square root, the quartic root. The quartic root is the data to the 1/4, okay? So, and we settled for the quartic root. So we have a new time series now, y star equals y to the 0.25, right? And that's this one. Okay, so this is what we're going to go with. That's the pre-transformation. And that's not going to show up in the ARIMA model, but that's something you need to keep in mind. Some people forget that they did this. And then when they forecast, right, they compare the actual data. What they do is they compare the actual data with the forecast. That and of course your forecast is going to be the quartic data, and then they're going to compare it with the actual data. And if you do that, notice how the numbers for the quartic is 4.8, 5.2, but the numbers, so it's going to look weird. And then you're going to say, oh, it doesn't look good, my forecast, but it's because you forgot that you did this transformation and you have to undo it at the end, okay? So let's see how many of you do that. I'll remind you. Let's see, now the time plots showed a trend in mean of quartic root. Okay, so we need to make the time series mean stationary. We tried different differences. And notice how I'm writing the differencing now, okay? I'm writing it already in polynomial form to prepare you for the algebra that's coming your way. So this is the first order regular differencing, okay? This is the second is the seasonal only, first order differencing, and this is the seasonal differencing of the regular differencing. And now I have a question mark for you, okay? Which one would you choose? I am torn between one or the seasonal or the seasonal of the regular. I don't know what to do, but since I like small models, I go with the they both look like the ACF of a stationary time series. And of course, you can argue, well, the seasonal looks a little more stationary because the higher lags, there is less, right? This one seems to have more inertia in the autocorrelations. So I tentatively go with the seasonal differencing, okay? That's my choice, okay. I could be wrong, right? But since I can go back and start again. So notice how I label my new variable is yt minus y star, because I did the quartic root, minus y star t minus 12. So I have this new variable, and that's the variable where I am going to settle, right? The seasonal difference. Okay. So now we identify a tentative model for the seasonal difference. Right. So the next step uses the seasonal difference. And the identification requires the PACF. So I do the ACF and PACF together to come up with a conclusion. And okay, I must confess that I did a little bit of data fishing behind the scenes here. And I tried different things, right? But my first identification didn't work. So let's suppose this was my first identification, okay? So this was my first identification, and why does that make sense? Okay, so let's look at the ACF. The ACF has significant autocorrelations for a few lags, except the second one is not. And the PACF also has some kind of smoothness to it, right? It doesn't just, but it cuts off faster, right? it cuts off faster than this one. So this one has significant 1, lag 3, lag 4, lag 5. Then at the seasonal, of course, I have a seasonal. The seasonal lag is the autocorrelation at the seasonal lag is significant. So I have a stationary time series, but still a random seasonal is there. And the PACF sort of, the PACF has less autocorrelations, right? And that are significant at lower lags, has the first and the third. So it has some kind of, it's not just the first and the second. So I'm torn between, you know, ARIMA. So, okay, I try ARIMA 2 for the regular part. Okay, significant. I could try 3, okay, but I'm gonna start with 2 because I like small models. And then an MA1 for the seasonal lag. The seasonal part, this one sort of cuts off, right? And this one has this one and this one significant, so that's the seasonal lag. So okay, more structure in the PACF than I do an MA1. Okay, so cuts off here very much faster than in this one. So I got an MA1. So MA1 for the seasonal, ARIMA for the regular. So this is my model at first, my tentative first model, although I told you I cheated a little bit, okay? Because I'm lecturing and I don't want to waste your time with all my searching, but you will have to do this searching, play with the small models at first. So here is an ARIMA and justify it based on your ACF and PACF. So I try, this is the notation, it's monthly data. So the 2 for the AR, this is the little p. I didn't do regular differencing, remember? So I have the little d equals 0, the little q equal 1. And then I did seasonal differencing. So this is the big D, this is the big P, and I have an MA1, so this is the big Q. So that's my model, and I feed it with the quartic room.ts, the order. It corresponds to the order there, and the order for the seasonal part is here, okay? So I fitted that model and I got this result, the output. So R gave me this result for this model. It gave me the AR1 coefficient for the regular part, the AR2 coefficient for the second, and I'm not gonna write the model for you because it's more complicated than that, okay? This is, the model is not written until the end, when you put it everything, the trend and everything together. So this is just keep it for now. Don't write a regression model because it will be incorrect. Okay, so then the MA1 part, okay, for so this is this part. So these 2 are for this part. And the seasonal MA1 is for this part, okay? That corresponds. And of course, like any good estimated model, it gives you the standard error of the estimates, okay? Because these are estimation of parameters of some model. Then it gives you the sigma square, and it gives you the log likelihood because it's the likelihood method that you learn in 100B. You maximize the likelihood. And then it gives you the Akeke information criteria, okay? So Akeke information criteria is going to be used later for model selection, okay? Later on, we choose, when we have several models, we are going to select the models using this criterion. We'll choose the one that gives us the lowest AIC, okay? But not just any models. They have to be models that satisfy the following, okay? After fitting, we check to see if the residuals of the model are white noise. So that's the first thing you have to do. Do these residuals have any other autocorrelation left that we didn't account for? Okay, so, okay, remember 5% of your ACFs, 5% of the R sub Ks will be significant just by chance, okay? So I'm not worried about having a few, 2 or 3 here and there. I have this one and then borderline there, okay? So I'm not too worried. This looks like the ACF of white noise, okay? Remember, the ACF of white noise has no significant autocorrelations, okay? So no correlation should remain after you feed a model because your model is supposed to be capturing all the correlation. That's why we're modeling, to capture the correlation in the data. And if you have any correlation left, that is here at the lower lags, okay? So you look here and you look at the seasonal. The seasonal has no significant autocorrelations. Here we don't even have any significant autocorrelations. So you look at lower lags, you look around the seasonal, there's no significant autocorrelation. Looks like the ACF of white noise. Okay, of course, remember white noise when you have finite data doesn't look like the theoretical one, but okay, we got a YCF. I'm happy. I see my model is a good model, gave me good residuals. The residuals are white noise. We capture all the autocorrelations, and therefore I can forecast with this model. So if the residuals of the model fitted are white noise, we can use the model to forecast. It's a good candidate. Okay, we keep that in our basket of models to compare later. Okay, so we'll always compare several models, and then we do the forecast. So as you can see, the forecast, this is the original training data. Okay, so this is the training data, and this is the test. I'm going to compare the test period data with the forecast. And since it's going to be very hard to see when you have all the data here, because it's nice to see the forecast compared to the rest of the time series, you see that it aligns pretty well. We did a good job. But it's also good to see it on its own. So you just select that period of the forecast, and then you are going to plot the actual data. Then you are going to plot the forecast, which is the red dotted line, and then the prediction intervals. You always are uncertain, right? You are predicting, you are estimating. There is uncertainty in everything you're getting. So we need to account for that uncertainty by using sort of the equivalent of confidence intervals. And these are called prediction intervals. It's one version of confidence intervals. And so you can see that all the data set falls around our confidence intervals, right? And that's our prediction intervals and the forecast, except maybe here at the beginning. So it looks good. I'm happy with my forecast, but hey, there is always the question: could I have done better? Right? So there is a next step. Okay, calculating the root mean square error of the forecast. So the data that we created with the model is here is the data. Okay, so this is the test data and our original data. Okay, and here. And here we have the prediction interval. Of course, it's called confidence interval because that's what it is really. The forecasted value for the data, the confidence interval high value, and this is the standard error of the forecast, which changes over time. Okay, and so we retrace our steps. We did quartic root, then we took the seasonal difference, then we identified a model, then we fitted the model, and then this is the algebra that's coming for you on Thursday. Then we'll have to do all this algebra to write the forecasting model for the quartic root, and then we'll have to undo the quartic root. Okay, so before we go, I'm going to show you I'm going to show you this other thing, the program. I'm going to show you the program and what is happening in the program, but you can run this on your own, okay? So everything that I have discussed is done in this program, okay? And you can run the program yourself. So you can see all the stuff that we have been seeing. But I want to call your attention to what happens after we forecast, okay? So this is all the stuff we've been, okay, here, I fit the model. But notice that I'm fitting the model to the quartic roots, okay? So the forecast, so I look at the residuals of the model, but the forecast is going to be, and then, you know, you want to make sure that your residuals don't have any stuff, but the forecast is going to be done on the quartic, okay? So the actual, you have to convert, okay? You have to convert the forecast of the quartic to the forecast of the original data. Yeah? And this is something you want to not forget to do, or otherwise you're going to see weird pictures of the forecast compared to the actual data, okay? So notice how the forecast that we get it's a list. So the forecast is going to give you the prediction, and it's going to give you the standard error, okay? And you're going to build the confidence intervals. But notice how the forecast value that you want to compare with the data has to be keeping in mind that you had the quartic root. You are forecasting, you are fitting the model to the quartic root. So you have to undo the quartic root for the forecasting and for the confidence interval. So when we create the prediction intervals, we are, and maybe we should call them prediction intervals, we are also undoing the square root for the intervals, okay? So the intervals are like any other intervals. Is the forecast minus 1.96, the standard error. The same way we build confidence intervals for any kind of estimate that we make, right? We use the estimate to do confidence intervals for the parameters. So here we do confidence intervals for the estimate for the actual data, right? And of course, we have to remember the pre-transformation, okay? I want to call your attention to this part because it's very important. Otherwise, if you don't do it later on, when you compare in the plot, the forecast, you say, oh my goodness, I did so horrible. Yeah, of course you did horrible. You just did, you're comparing rooms who have units 500 and so on with forecasts that have units 4 and 5. So your forecast will be at the bottom of the plot and your your data will be at the top of the, so that's not good, okay? So if you are not sure, just try not to put this here and you'll see what plot you get. Yeah? So I'll post this so you can see the plots and the, I don't know if I run everything. I want to make sure. Yeah, so you can just run it yourself. Okay, so you got the predictions, the confidence intervals, and then you do the plots yourself. Okay, and you can use this as a template for things that we are going to be asking you to do also in the quiz and in the future homeworks. Okay, so this is a good template for you to fit ARIMA models. But of course, there is a lot of work you have to do yourself. It has to be well done, okay? All the steps and justifications and so on. So what we'll do on Thursday in the next lecture is going to be to then pass from having done the work to communicating the work, okay? To communicate the work, we have to write a mathematical model. And that involves more of the algebra of differencing and the backshift operator and the algebra of ARIMA models and understanding invertibility and stationarity a little more, okay? So Thursday will be a little more theoretical, although we will do another example, okay? So I have office hours at 11:15, but I want to stop this now here. And if you have any questions,